will explain Chapter 9, Sections 9.1 through 9.3 on radicals. Section 9.1 focused on square roots. 2 is the square root of 4 because 2 times 2 equals 4. So when we're shown a radical sign, we are looking for a number that multiplies by itself to equal the value under the radical sign. The number under the radical sign is called the radicand. The principal square root is the non-negative square root. Negative 4 is a square root of 16 because negative 4 times negative 4 also equals 16. So if we're looking for the principal square root, we're looking for the positive number of 4. The square root of 16 would equal positive 4 as well. For all non-negative numbers, n, the principal square root of n is written, the square root of capital N, is defined to be the non-negative number a, if and only if a squared equals n. Let's find the square roots of the following values. For the first number, we're looking for a positive number that multiplies by itself, or squared, equals 121. And that would be 11. 11 times 11 is equal to 121. We can also think, what number squared equals 121? On your calculators, many basic scientific calculators do have the radical symbol to do square roots. So you could type in radical symbol, your number, and press equals to get 11. Then in this case, B, we're asked to find the square root, but then take the negative value of it. So it's not the principal positive. 10 times 10 is 100, but then we're making that value negative. So negative 10 is our answer. And in this case, when we have a square root of a fraction, what we end up doing is taking the square root of each number individually. So we'll ask ourselves, what is the square root of 16? And what is the square root of 49? And 4 times 4 equals 16. 7 times 7 equals 49. So our answer would simplify to 4 over 7. If we have decimal values, we can do the same thing. For a second, just ignore the decimal. Look at our number of 9 and ask yourself, what number times itself equals 9? Well, 3 squared equals 9. 3 times 3 is equal to 9. 9 is not a whole number here, so I have to consider it is in the hundredths place value. And 2/10 would equal 1/100. 10 times 10 is 100. So my 3 would be in the tenths place. Second example, 5 squared equals 25. But here I'm not just dealing with a 25, I'm dealing with 2500. And I know 10 times 10 is 100 to give me those 2 zeros. So the square root of 2500 would be equal to 50. We can use calculators to approximate if our values are a little bit harder. 32 is not a perfect square, but I know 5 times 5 is 25. 6 times 6 is 36, so I know my number falls between 5 and 6. And to get that value, in this case, it would be a lot easier to use a calculator. And rounding to the nearest thousandths place would be the third decimal to the right, or the third place value to the right of the decimal. Tenths, hundredths, the 7 is in the thousandths place. So if I'm looking at my calculator screen, I can go tenths, hundredths, thousandths. The 6 was actually there, but I need to round. So I take a look to the right of the 6 and I see an 8. And since that number is a 5 or higher, I would round that 6 to a 7. Tenths, hundredths, thousandths, we have a 2. Look to the right, I see a 6. That 6 is bigger or 5 or greater, so I'm going to round up to a 3. So 14.213 or 213 thousandths is the approximate square root of 202. Moving on to section 9.2 on simplifying radical expressions. If we're asked to simplify a radical expression, a lot of times you'll see a radical expression if there is a number raised to a power, then we can simplify that. What do we notice here in this first example? We're asked to take the square root of 81 and also square 81. Well, this is like saying multiply by 2, take a number, 7. Multiply that by 2, and then I'd like you to divide that by 2. What do you notice? Well, we end up with the same answer of 7 because what happens is that a multiplication and division cancel each other out. And that's exactly what's happening here. Take the radical, take the square root of 81, take the square of 81. Those cancel each other out, so our answer is equal to 81. In the second example, we're taking our number 75 and raising it to the 4th power. And using what we learned earlier, we can say, well, this is the same as saying 75 squared. And 2 times 2 would give us that 4th power. So I can take the square, take the square root. Those would cancel, and I'm left with the answer of 75 squared. Here are 2 more examples to simplify. Think this is a square root, so I need to figure out what is this raised to the power of 2. And remember, when we're multiplying powers, those numbers of exponents are being multiplied to equal 8. So 2 times what number equals 8? That's 4. So z to the 4th power would be our answer here. Same thing here. What 2 numbers equal 20? 2 has to be one of them, so the other one is 10. So that remains, gives us x to the 10th power because the 2 and the square root cancel. What if we're asked to multiply and we have numbers that are under a radicand or they're square roots? All we end up doing is multiply those 2 numbers and then we can find the square root. These are all equal to each other. We can multiply them first, or we can break it apart and show each one being multiplied individually with the square root symbol still staying with that value. In cases where we have variables and numbers, we can actually break this apart to find the square root of 81 and then cancel out our exponents. If this was 4 times 2, the 2 would cancel and the square root would cancel. So we'd be left with 9c to the 4th. And in this case, we can break these x, y, and z apart to, again, try to cancel square roots. So we're left with a 2 here, and 2 times 5 is 10, so this would be a 5. And all the square roots would cancel with those powers of 2. Simplifying, we know that perfect squares we can simplify. So with this first value, we can say, well, 50 is not a perfect square. So what numbers multiply to equal 50? 5 times 10, 25 times 2. 25 is a perfect square of all those 4 numbers that were listed. So we can take the square root of 25 and then keep the square root of 2 because we can't break that down any further. 48, we can say, well, that's 4 times, 4 is a perfect square. 4 times 12. Is there anything bigger than 4 that's a perfect square? 5 is not. 9 cannot. Going down, 3 times 16. 16 is a perfect square. So we'll use that value. That would be a square root of 16 is equal to 4. Keep the square root of 3. We can't simplify that any further. We can do the same thing even if we have variables. So 5 times 4 and 1, x plus 4 plus x plus 1, x to the 4th power plus x to the 1st power would equal x to the 5th power. So we can break these apart into what we would add together to get that exponent. And then we can find the square, 4 squared. would be 2 to the second power would equal 4. So then those exponents in that 2 would cancel out. And then with our x's here, we can break this into an even number. So we could take out that square and also make this into an even number by taking out that square. So we'd have x and y both raised to the first power. And then we can simplify that further by saying, well, 6 times 3 is 2. Then our square root cancels. 5 times 2 is 10. That square root cancels. I'm left with 5. X stays the same. We can't simplify this radical any further. And y stays the same as well. And since both of those numbers are under our radical sign, we can combine them as x times y on the inside. One more asks to simplify. We can break 48 down into two factors. 16 times 3, we can find the square root of 16. The 3 is still under the radicand here. It cannot be simplified any further. The 15, we want to make that into an even number. Sorry, my brain went for a second. So we would take away our 1 to make that 15 even as a 14 and say 7 times 2 is 14. So that's why we have a 7 here. The 2 and the radical sign canceled out. And we're left with our 3x both under the radical sign and the 4 times 7, x to the 7th on the outside. In our last section, 9.3, we're looking at adding and subtracting radical expressions. Like radicals, all radicals having the same radicands can be added just like you add like terms. So look at these examples here. Square root of 2, square root of 2. Well, we can combine our like terms. 5 plus 4 is 9. Both of those values were being multiplied by the square root of 2. And so it doesn't matter if we add first and then multiply by the square root of 2, we would get the same answer. And the same rule applies for the second example there. So let's try combining another one. So we have 5 times 2a, looking for common numbers and variable combinations underneath our radicals. So we can combine the 5, a positive 5, and the positive 3 can be combined together. And that would give us 8 on the outside, right here, and 2a on the inside of our radicand, and plus 3a minus 7 times the square root of 2. These cannot be combined because the number under our radical sign here is not the same. We have an a and a 2. All right, let's try to combine this further. So we want to break down our values to say, can I break 50 down into two numbers where one of them is a perfect square? Yes, we can. 25 times 2 is 50, and 25 is a perfect square. That equals 5. Can we break down 27? Yes, we can. 9 times 3 is 27, and 9 is a perfect square. Square that out. 3 times 3 is 9. And same thing with 12. 4 times 3, 4 is a perfect square, and if we square 4, we get 2. So our numbers that remain will stay under our radical signs. These two have the same, so we can combine our 2 minus 3, and our 5 would be, remaining here, so we'd be left with, it just depends on how you would want to write your answer, but you could write it as the negative radical of 3 plus 5 times the square root of 2, or you could do it as 5 times the square root of 2 minus the radical of 3. Either way, it's the same thing, only they're written in reverse order. And just a few more examples here. Combine 44, the square root of 44, plus 2 times the square root of 99. So look for those perfect square factors. Once you have found those, in this case, 9 is a perfect square, and 4 is a perfect square. Then simplify. They both have radical, or the square root of 11 that they're being multiplied by. So we can end up combining the numbers on the outside and adding 2 plus 6 to get 8. In our last example here, combine any like terms that we can. In this case, the first thing we want to do is simplify those numbers and think of numbers that are perfect squares. 25 is a perfect square. And in that case, that 25 can cancel out 2 of 5. We're left with 2a, 2a, and we can break the 36 down into, it already is a perfect square. 6 times 6 is 36. So what does that leave us with? 2a. So all of these have the same numbers underneath our radical sign. So we can do 5 minus 3 minus 6 to get negative 4 times the quantity 2a square rooted.